Okay, so today we're going to look at the trapezoidal rule 5.5. That's not a mistake. We actually skip through 5.2, 5.3, and 5.4 for right now, so we can do trapezoidal approximation method. If you did not watch the screencast and do the notes for 5.1, please make sure you go back and do that first, okay? Because I want you to understand the process for the rectangles before we look at trapezoids. So trapezoidal approximation is actually the more common one that is used throughout calculus to approximate the area under the curve. And with the trapezoids, the difficult part is that it's almost like if you think of them on their side. So if you think of, you have a flat base and your trapezoid, your trapezoid is like this. So we know that in a trapezoid, hopefully you remember the height over 2 and then base 1 plus base 2, or 1/2 times the height and then base 1 plus base 2. So whenever we refer to the height, we have to make sure that it's perpendicular to the base. So the height is not going to be the height like when we looked at the rectangles. The height is actually your subinterval length. And here's your base 1 and your base 2. So it's kind of like looking at a trapezoid on its side. Okay, so if you can imagine that. And notice we don't really need to know the value of this slanted portion. So if I wanted to figure out the area of this trapezoid, we'd take whatever the height was, and then we'd divide that by 2, and we'd add base 1 plus base 2. Now, imagine that if we had a curved portion. So let's just look at this part of the graph here. Let's look at from here to here, or actually, let's go over from here to here. Let's just say I want to focus in on this part of the graph. This is kind of complex. Don't worry about all this notation. I think this is actually a complicated graph, and I probably should have just copied and pasted just this one portion. So I'm going to focus in on from here to here. So if you look at where these spots hit, so like looking at this first one, okay, here's my first trapezoid. Here's the height, and then I have base 1 and base 2. But when I go to do the next trapezoid, so I have the same height, but I have base 2 is really my base 1 for this next one. And then I have a base 3. So I end up using base 2 twice. And then when I do the next trapezoid, here's my height again, and I have base 3, and I have like a base 4. So base 3 was used twice since it was part of this trapezoid and this one. So when we put this all together, so let's just say we had this, the area under that curve would be approximated by the height over 2. We only used base 1 once for this region that I was focusing in on, but we used base 2 twice, okay, for this one and this one. We used base 3 twice for this one and this one, but we only used base 4 once. So it's kind of like, it's not really, it's a little bit easier than taking each trapezoid and adding it separate. And that's basically where the trapezoidal approximation method comes from. Okay, so one of the things I just talked about was that the height is the length of each subinterval. So this is the complete opposite of rectangular approximation, whereas the bases are the function's value at each base endpoint. Okay, don't worry about this notation right here yet. We will talk about that later. So here is the trapezoidal rule. So you'll see I used notation with y. So just think this is the first endpoint that we would see. And notice all the ones on the interior, because these are interior trapezoids, are all used twice. And then the last one is just used once. So the first and the last are used once, and all the ones in the middle are twice. Just kind of a side note, if you took LRAM and RRAM and you took the average, you would have trapezoidal approximation. Okay, let's do an example, because I think it'll make more sense when we see the example. We're going to refer to the region R enclosed between the graph of the function, between the graph of y equals square root of 2x and the x-axis from 0 to 8. Okay, so we have 0, 0. When I plug in 2, I get 2. Plug in 8, I get 4. We could graph more, but I'm just going to, just to save some time. Here's the graph. That's what we're going to approximate. Now, notice it says here 4 subintervals of equal length. So that means if it goes from 0 to 8 and there's only 4 subinterval, the subinterval length has to be equal to 2. Now remember, that is the height. So basically, this is what our trapezoidal approximation looks like. So it was h over 2, so it ends up being 2 over 2. So the first one will go from 0 to 2. That's our first subinterval. Now, if you notice, it actually looks like it's actually a triangle, but we could still apply the same rule, so it's fine. So we have 0 plus, now 2 has a height of 2. So that's base, think of that as, that's our second number. But remember, when we look at our next interval over from 2 to 4, this is used twice, so we're going to do 2 times 2. Next one is at 4. So notice this is used twice, this is used twice, this one's going to be used twice. And this here and here are just used once. Okay, so basically I need to have 2, and then this is going to be square root of 2 times 4. Remember, our graph was y equals square root of 2x. So that's where this 2 came from, by the way, and that's where the 0 came from. Plus, next is 6. So it's 2 times square root of 2 times 6. Plus, finally, square root of 2 times 8. That one's only used once. So I have 4 plus 2 times square root of 8 plus 2 times square root of 12 plus square root of 16, which is 4. We can approximate for that. That's fine. Just make sure that you round to the nearest thousandth place, so 3 decimal places. So take a minute, plug that in. We should get about 20.585. Okay, here's the next one. This one, the graph's already there. So this time we have 4 subintervals. Oops, don't want that color. 4 subintervals from 0 to 2. So that means we have to use the half points. Okay, so trapezoidal approximation. So notice each subinterval is a length of 1/2. So my height is equal to 1/2. So my trapezoidal approximation is going to be 1/2 divided by 2. Now remember, we're going to plug in, so imagine this is going to determine our bases. Now remember, 0 and 2 get used once. But the rest of them, the 1/2, the 1, the 3/2, we're going to have to multiply by 2 after plugging in, that is. So basically, this is what it would look like. Here's our first trapezoid. Oops. Then from here to here, from here to here. Okay, so we want to find the areas of those trapezoids. So here's the bottom line is you could do this the long way and you could just figure out the area of each trapezoid. But that's where the trapezoidal rule is supposed to kind of make it easier. But it's completely up to you. If you want to do it the longer way, that's fine. Okay, so here, if I plug in 0 into, so it's basically negative 0 squared plus 4 plus, now I'm going to have 2. So if I plug in negative 1/2 squared plus 4, and I'm plugging those in, 2 times, oh, you know what, I don't want the negative sign like that. So then I have negative 1 squared plus 4, and 2, and negative 3/2 squared, that's right, it should be like that, plus 4, and then plus, the last one's just used once, so it's going to be negative 2 squared plus 4. So go ahead and add all of that up. So add all that up. And I get 5.25. So double check, make sure that that's what you got. Okay, the next example, we have a table of values. An observer measures the outside temperature every hour from noon until midnight, and recording the temperatures in the following table. What is the average temperature for the 12-hour period? So first we're going to do the trapezoidal approximation to find basically all the values of the temperatures over the time interval. Noon is 0, midnight would be our 12. So if we look at this time interval goes 1 hour, increases at 1 hour each. So our height is equal to 1, so it's 1 over 2. The first one gets used once, and all the ones in the middle, in between, get used twice. So it's 2 times 65 plus 2 times 66 plus 2 times 68, and so on. Go down here. Now, once we get to the 58, the 55 is only used once. So take a minute to plug that all in. You should get 782. Now, since we're looking at the average temperature over the whole 12-hour period, we're basically going to take 782 divided by 12 so that we can get like the average over the whole entire 12 hours. And that's going to be 65.5 167. All right, so next we have a sled that's moving along a track. Okay, until friction and the unwinding of a rubber band gradually slow it to a stop. A speedometer in the sled monitors the speed, which is recorded at various time intervals. So find the estimated distance traveled using trapezoidal rule. So if you notice, the time intervals here are all 0 to 2 seconds, 2 to 4, 4 to 6, and so on. So h is equal to 2. So height over 2, so 2 over 2. And then here are all my numbers. So 5.4 is used once, and the rest of them are used twice. I know, it's just kind of copying down, but this feels a little like busy work. And the last one, the 0, is just used once. So take a minute and plug that in. And we should get 57. So total distance traveled, and this was seconds and feet per second, so 57 feet. And then the average speed, so the time interval went over 18 seconds, so 57 over 18, and we get about 3.167, and that will be feet per second. Okay, so again, there's the worksheet, assignment number 33. That's going to be for tonight. And then on Monday, we'll review assignments 32 and 33, and then we'll move on to the next lesson. And I will post solutions to the homework assignments, so you can also check those as you go.